In this video, we shall look at the region proposal network in detail, which is one of the component of the Faster-RCNN pipeline. In my previous video on Faster-RCNN, I gave an overview of the Faster-RCNN algorithm and briefly discussed the entire pipeline. If you have not watched it, I recommend you to have a look at it. I have provided the video link in the description. Even if you have not watched it, you can still understand this video as I will start with a very quick recap of the required information. So let's begin. In my previous video, I briefly mentioned that the region proposal network outputs several region proposals, each with an objection score. And to do that, we define a set of k number of reference boxes called anchor boxes at each location having different scales and aspect ratios. And we have seen that the k is equal to 9 in the paper. Now the task of the region proposal network is to predict offsets with respect to each anchor box and also predict the objectness score. As an example, I had shown that to obtain white box shown here as the output region proposal, the region proposal network predicts offsets to the red anchor box as shown here. Having predicted these values, we can then obtain the XYWH of the region proposal. The concept of anchor boxes is a novel concept introduced in the Faster-RCNN paper, which directly allows us to obtain multi-scale boxes. Previously, people were using different schemes for addressing multiple scales and sizes. For example, pyramids of images and feature maps or pyramids of filters with multiple scales and sizes were used, which were very computationally expensive. But anchor boxes directly allows us to obtain multi-scale boxes without much computation. So it was a very novel technique which was introduced in this paper. Let us now try to understand the architecture of the region proposal network. Here, the input image is first passed through a set of convolution layers which obtains feature maps. These feature maps are then used by the region proposal network to obtain two output branches. Let us now try to interpret the output branches. We can interpret the output as follows. For a set of k anchors present here, we have corresponding output vectors in both the output branches. The 4k dimensional vector in the first branch represents 4 parameters of the bounding boxes for each of the k anchors. Similarly, 2k dimensional vector in the second branch represents the probability of object and no object classes for each of the k anchors. Having interpreted the outputs, let us now go inside the region proposal network. Here at first we have 3x3 con layer where we have 256 number of 3x3 filters, each having a depth of 256. This gives us 256 dimensional output feature maps as shown here. This is then given to two 1x1 con layers as shown here, where in the first 1x1 con layer we have 4k number of 1x1 filters, each having a depth of 256. Whereas in the second 1x1 con layer we have 2k number of 1x1 filters having a depth of 256, which gives us the outputs shown on the right. These 1x1 filters can be interpreted as fully connected layers as shown next. For example, let us consider a fully connected network having 256 input nodes. To obtain one output node, we perform linear combination of 256 input nodes. This operation is similar to that achieved using 1x1 filters, each having a depth of 256. Thus, we can say that we process each 256 dimensional vector using fully connected layers which are shared across all the 256 dimensional vectors corresponding to the respective set of k anchors. In order to train the region proposal network to predict offsets and the objectness score, we need to first define the ground truth. This is done as follows. A positive label is assigned to two kinds of anchors. First, the anchors with the highest intersection over union overlap with a ground truth box, and second, anchors that have an IOU overlap higher than 0.7 with any of the ground truth box. A negative label is assigned to a non-positive anchor if it is lower than 0.3 for all the ground truth boxes. By ground truth boxes, we refer to the final output bounding boxes for all the objects in the image. Anchors that are neither positive nor negative do not contribute to the training objective. Now, to train the network, we also need to have ground truth proposals for each positive anchor. But if you understand, we only have final ground truth bounding boxes for the objects. We do not have the ground truth proposals for each positive anchor directly. Hence, we need to create pseudo ground truths, which is done as follows. For each positive anchor, we check which ground truth bounding box has the maximum intersection, and then assign maximally intersecting ground truth bounding box to each positive anchor. This becomes the ground truth region proposal for each positive anchor, using which we can obtain the ground truth parameters as shown here. An interesting point to note here is that one ground truth bounding box can get assigned to multiple positive anchor boxes. Having defined the anchor labels and the ground truth parameters, we are now ready to understand the loss functions. Since we have two output branches, each responsible for a unique task, we have to define two different loss functions. Let us consider the first one. I mentioned that for each of the k number of anchors, we predict two values which represent probability that an anchor contains an object and the probability that it does not contain an object. You might have guessed this is indeed a classification problem with two classes. The expression for loss function is as shown here, where I is the index of an anchor and Pi is the predicted probability that an anchor I contains an object, and Pi star is the ground truth, which is 1 if the anchor is positive and 0 if it is negative. This is basically a log loss or a cross entropy loss over two classes. Let us now consider the second branch, which is basically a regression task which predicts bounding box offsets. The authors proposed a novel loss function called smooth L1 loss, which combines L1 and L2 loss as shown here. Here also I is the index of an anchor, Ti is a vector representing the four parameterized coordinates of the predicted bounding box, and Ti star is that of the ground truth box corresponding to a positive anchor. This smooth L1 loss is less sensitive to outliers, as we can see from the expression. Having defined the loss functions, let us now consider the training procedure which is used to train this RPN. The RPN can be trained end-to-end by backpropagation and stochastic gradient descent. In the paper, they follow an image-centric sampling strategy to train the network. That is, each mini-batch consists of anchors which are sampled from a single image where the number of positive and negative anchors have a ratio of up to 1:1. If there are fewer than 128 positive samples in an image, they pair the mini-batch with the negative one. Thus, in one iteration, a mini-batch consisting of 256 anchors which are sampled from a single image is used to train this network. Once it is trained, RPN can produce several output proposals, but these proposals highly overlap with each other. To reduce redundancy, we apply a technique called non-maximum suppression to remove unwanted or unimportant region proposals. NMS does not harm the ultimate decision accuracy but substantially reduces the number of proposals. After NMS, we use the top n ranked region proposals for detection. So this comes to the end of this video on region proposal network. I hope this video was informative. If there are any questions, suggestions or comments, please let me know in the comment section below. In the next video, we shall discuss in detail the Fast-RCNN detector, which is the second component of the Faster-RCNN pipeline. So see you soon in the next video. Thank you very much for watching this video.